So here we're looking at making predictions either from the scatter plot or the graph, or finding the regression line and then predicting from that equation. We'll do from the graph first. So what you need to do when you're predicting from the graph is you rule a line from what you're trying to make a prediction for to the line of best fit or to your regression line. You then rule that over the other axis to find the predicted value. So we've got a scatter plot down there on the bottom left-hand corner. We want to predict for sales for a 20-degree day. So find where it's 20 degrees on one of your axes and rule a line in. You'll find at some spot that goes through your line of best fit. And if you rule across to your other axis from the point it meets your line of best fit, you'll see the predicted drink sales was 100 drinks when the temperature was 20 degrees. This is useful because you can do it at any temperature and you can find its predicted drink sales from there. Predict the temperature required to sell 120 drink sales. So we're trying to predict the temperature when drink sales is 120. So rule a line from drink sales as 120 and then rule down to the other axis. And you can see it fits somewhere there. Now I know that this point just here is 24, this point is 28, so this point has to be 26. So if that's halfway between 26 and 28, then it's going to be approximately 27 degrees. Now this is useful because it's quick and it's easy and it's just ruling up a couple of lines. But the problem with this method is, how do we know how precise it is? Do we know if that is actually 26.8, 26.9, 27? It could be 26.95. We've only got a fairly good approximation. We're not real precise. So from the graph is perfectly fine. It's something we need to know how to do. But if you want to be more precise, we have to predict it from the regression line. So from the equation, we substitute the values into it. So I've already found the regression line for that thing that was there, and its drink sales is 46.15 plus 2.73 by temperature. Predict for the number of sales on a 20-degree day. So your 20-degree day is your temp, so you change temperature to 20. So for the first one, I'm just going to call it D for drink sales, 46.15 plus 2.73 by 20. Now I'm going to pause the video for a second, work that out on a calculator and write down what it should be. And I found out that it's 100.75. So if you had to round that off to the nearest whole number of drink sales, you would have 101 predicted drink sales. So we can say that that is roughly equal to 101 drink sales. So even though it looked like 100 on my graph, it's a little bit more precise using the equation, and we end up with the 101. So predict the temperature required to sell 120 drinks. So this time drinks is 120, so we can change the drinks to 120, which equals 46.15 plus 2.73 by temperature. Now, I can backtrack like I would have done in year 10. If you know how to backtrack, perfectly well and do it. Or there is the solve function on your calculator. If you're not sure about the solve function on your calculator, I'm going to bring it up and then show you how that works. Okay, now these are called CAS calculators because they can do computer algebraic system, right? They can solve algebra. So we've got this problem. We want to go into a calculator page, and what we want to do, we want to tell it we want to solve it. So you can use the keys down the bottom and type the word solve. That works fine. Or you can go to menu, algebra, and go to solve. Sometimes this numerical solve helps if your answer doesn't make a lot of sense, but generally solve works fine. Now we need to tell it what we're trying to solve. So we're trying to solve 120, which equals, when I find where the equals button is over there, 46.15 plus 2.73 and times by t. That's what we're trying to solve, but we have to tell it what we want to solve. We want it to find t, so we use the comma t, and that means we solve that for t. Close your brackets off, press enter, and it tells us that t was 9.55. Okay, so when I quickly look back, I've seen 9.55 doesn't make sense. It doesn't fit what we found before when we looked at that regression line. So when I look back at it, I actually should have written down that it was 2.73, not 7.73. This is where your CAS calculators are really good. If you've just made a mistake and you need to change something, your best bet is to go up and highlight the thing that you had, press enter, it will move it down, and then you can just change where you made the mistake. 27.05 definitely more matches what it should have been, and that's what my prediction should be. Whoops, so I shouldn't write in the answer. t equals 27.05. Right, and we've done our predictions from our regression line. It's more accurate, but it takes a little bit more time to do. Two words that you need to know, and these really should go in key terms that you must understand, is interpolation and extrapolation. Interpolation is taken from within the data given. So if you have got a scatterplot and you're trying to make a prediction for this point here, it's within the data. This is where our data starts, this is where it finishes. It's within that, it is interpolation. Extrapolation, if you've got your scatterplot, looks like this, right, and you're trying to make a prediction over here, then this is extrapolation. It's outside the data. Now, there's 2 points that you need to make for this. Interpolation, all right, is reliable, and extrapolation is unreliable, but we'll cover that a little bit further later on. Also, if you're actually told the numbers, if your data goes from 2 here to 10 and you're trying to predict for 4, then it is interpolation. If your data goes from 2 to 10 and you're trying to predict for 20, then it's extrapolation. Now, a note here, if your textbooks ask for the limitations of the prediction, it is asking you to state whether the prediction is reliable or not. This is part that goes with that, the reliability of a prediction. For a prediction to be reliable, you have to have a strong correlation, whether that's an R value of 1 or -1. So what it means is if you have something which looks like this and you predict, it will be more reliable than something which looks like that, because your line of best fit fits the data. So if you predict it's going to be very close to everything else, your line of best fit in this one doesn't really fit the data, so it's not going to be as reliable to the other points. Predictions must be interpolation to be reliable. So for this one, if you predict within here, it's fine, but if you predict out here somewhere, what's to say that this data doesn't slow down and change? An example I always use is people's height. If you're predicting the height for a 16-year-old from a group of, say, 14 to 20-year-olds, it's probably going to be fairly reliable. But if you try and predict a 50-year-old, they're going to have stopped growing at some point. So their prediction's not going to follow that straight line. And the more data points it's got, the more reliable your prediction will be. Because the more data points you got, the better you'll see your straight line, the better you'll find your line of best fit. Don't worry about that extra bit of animation. I don't know what that is. Now, interpretation of your regression line. These are really important to have down in your notes as well. What you've got 2 points. It's what we call A and B, right? And it's always in the form of y equals A plus bx, because this is what we use in year 11 and year 12. The first part, the A value, or we'll do the gradient first, the B value. So the second part, the B value, tells you the gradient. It tells you how much the response variable changes for every one increase in the explanatory variable. So we remember that your Y is always response and your X is always explanatory. So in this case, my height was response, my age was explanatory, and this tells me it is expected that someone grows 2.5 centimeters for every 1 year. When you write up your conclusions to these, write the variable names in. Don't just say that we expect the response to increase by 2.5 for the explanatory. Say we expect the height to increase by 2.5 for every 1 increase in age. And the number at the front is your y-intercept, which is A, and this tells you what we expect the response variable to be when this is 0. So it's expected at birth or at age 0 that someone will be negative 25 centimeters tall. This doesn't make sense, so you just say it's unrealistic due to being a negative number. One more example with those is we've changed the number slightly, and this is going to help you particularly with question 6 in your textbook. The gradient now, if this is age over 20, it's the same as saying 1 times age over 20, which is the same as 1 over 20 times age. So this time your A value is 1 over 20. And we can say that we expect the height to increase by 1 over 20 for each increase in age. If you want that as a decimal, do this 1 over 20 as 1 divided by 20, which is 0.05, and that will be your decimal in here, which then could be written out as height negative 25 plus 0.05. 0.05 by age. And then again, you could say we expect this person's height to increase by 0.05 meters for every one increase in age, and the y-intercept has not changed.